Hey everyone, today we're going to continue our discussion about kinematics and specifically how acceleration relates to the motion of an object and what exactly or how exactly it's going to change the motion of an object. So acceleration, we've talked about it a little bit, more specifically acceleration, which we represent with the variable lowercase a, is the time rate of change of velocity. And to kind of simplify that, all that really means is that acceleration is how velocity is changing over time. We represent that with a simple formula, delta V over t, so the change in velocity over time. And that's going to give us an interesting unit here, meters per second squared. Meters per second, considering we have our change in velocity, which is meters per second, and our time, which is also in seconds. So we end up with a meter per second squared, combining our like terms. Now, if we consider an object that is accelerating uniformly from some initial velocity to a final velocity, or initial speed to final speed, we could look at that motion and the average velocity as the initial velocity plus the final velocity, and we'll simply divide that by 2. Now, that doesn't necessarily mean that the object is accelerating or its speed is exactly the average speed the entire time. That's going to depend on the acceleration, but it's going to give us an idea of how quickly that object is moving. So we're going to look at a couple different graphs here, see how acceleration relates to motion on our motion graphs. We'll start with speed versus time, where we'd have speed and time. Let me fix that t. Time would be on our x. And if we consider this will be our 0 speed, and we'll consider a positive value in the first quadrant. And this horizontal line, again, which has a slope of 0, this is going to indicate constant speed. We have no change in the speed. The value is what it is. There's no change. The object that's moving is going to stay at that speed until we do see a change in the graph. With constant speed, it also means that there's no acceleration. If we were to compare two here, again, our axes are going to be the same. We'll have our 0 line here. Put this over on the side here. If we compare the speed of two objects, let's say object A, and let's say object B, of those two, which one would be traveling at a faster rate of speed? Well, we know that they're both constant speed. We don't have any change in the slope of our line. But A is moving faster. Its value is higher up on the y when compared to object B. And again here, our acceleration would be 0. There's no change in the slope of our speed versus time graph. Now if we look at two other objects, let's consider object C. And let's go with object D. Again, these are both straight lines. A little hard to draw here, but those are both straight. If we compare the motion of C and D, what's the magnitude of the speed? Which one has a greater magnitude of their speed between C and D? Well, if we were to simply kind of compare how close either of those graphs of C and D are to our 0 speed point, C would be closer, which means C has a slower speed, or D is moving faster. Again, these are both at constant speed. Slope is not changing. And because of that, our acceleration is still 0. So D would be moving faster. Considering the speed is negative, the sign of the speed for D is negative, D would be moving in the opposite direction of C at a faster rate. This might be something like, let's say, -4 meters per second. Maybe this one is a +2 meters per second. Again, the sign indicating direction. So a straight line with a positive slope is going to show increasing speed. Or constant acceleration. Remember, acceleration is how velocity or speed is changing over time. So if our speed is increasing, we have to be accelerating. Again, we'll consider time on our x, speed on our y, and we'll graph this as object E. This is a steadily increasing slope, so acceleration must be uniform. So the slope of this line is acceleration. The slope of the line equals our acceleration. And that's because the slope is speed over time. Changing the y over changing the x. Now a straight line with a negative slope is going to show the opposite, which is decreasing speed. Or constant negative acceleration. Which we would also call deceleration, which is going to slowly bring the speed down or quickly, but it'll bring the speed down of our object to a certain point. Now again, we'll look at speed on the y, time on the x with our 0 point here. And let's consider object F. So again, we have uniform deceleration, indicated by the negative slope of our line. The negative slope is going to give us a negative acceleration. Or deceleration, however you want to refer to that. A line that's going to cross the horizontal time axis is going to cross that 0 point on the y. Is going to indicate a change in direction of the object. Meaning that the speed in one direction is going to decrease to 0 at the time when that line is intersecting the horizontal axis, and then it's going to increase in speed moving in the opposite direction. And this is all in relation to our starting point, our 0 point, and that's going to vary depending on the situation. So we're going to use a little line here. We'll talk about, well, let's set up our graph first. This is going to be speed. This is going to be time down here, but I want to keep this out of the way, so we'll put this over here. We're going to consider object G, and we'll consider 3 different points here. One, 2, 3. Now the first part of our line here from 1 to 2. So from 1 to 2, we have a decrease in speed indicated by the negative slope of that line. At point 2, our velocity or our speed equals 0. We change direction. We have to stop moving in one direction before we can start moving in the other direction. From points 2 to 3, we now have an increase in speed as our velocity gets more negative, but again, the negative indicating the direction, so we have an increase in speed in the opposite direction. The magnitude of our velocity is getting higher. The sign is negative, but that is just indicating our direction. So at point 2, we change direction and we start to increase our speed in the opposite direction. A curved speed timeline indicates that acceleration is not constant. And again, this will be speed, time, and a little curved line here. This might be H. We're going to see with that curved line, our speed changing not uniformly is going to indicate an increase, in this case, an increase in acceleration. I'm going to give you 2 examples here of how we can look at motion of an object graphically, determine acceleration, and determine how far the student's going to travel in the given amount of time. And we're going to try that in 2 different ways. So we use the same example for both. A student's coasting downhill on a skateboard at an elapsed time. I'll put some numbers in here in a minute. At 1 second, the student is traveling at 3 meters per second, and at 6 seconds, traveling at 13 meters per second. So let's set up a graph here to show this. We're going to do speed versus time. We'll put time down here. We have to go from 1 second to 6 seconds. We'll start with a 0 here. 1, 2, 4, 5, 6. And we're going to put speed over here on the Y. We span from 3 to 13. So we'll call this 0. And let's go with 2, 4, 6, 8, 10, 14. And we're just going to graph this real quick. At 1 second, the student's traveling at 3 meters per second. At 6 seconds, at 13 meters per second. So there. It's about as straight as I'm probably going to get it. Determine, let's try the first one here. Determine the magnitude of the student's acceleration. Well, this is a uniform looking graph. The line is consistent, it's straight. We connect 2 points. There's no curved line there. We can assume the motion is uniform. Now if we're looking for acceleration, we know that acceleration is the change in velocity over time. And the change in velocity, well, change would be Vf minus Vi over t. We end at 13 meters per second, and our initial was 3 meters per second. And the time that it takes for that to happen is 5 seconds. So we subtract these two. Seconds cancel. We're left with an acceleration equal to 2 meters per second squared. Excuse me, these combine, not cancel. To determine the average speed of the student, according to our reference table, if we have a uniform motion of an object, we can just add the initial and final velocities together and divide by 2. Initial velocity, 3 meters per second, plus the final of 13 meters per second, divided by 2. This comes out to 16 meters per second over 2. We get an average of 8 meters per second for our speed. Put a box around these. This is also, the average here is also going to be the midpoint of our line. So to determine the distance traveled by the student during the elapsed time, we can use the relationship between distance and time, which is average velocity. And if we rearrange that and we solve for d, what we end up with is that distance equals average velocity times time. Plugging in for this, we take our average velocity, 8 meters per second, and we multiply it times 5 seconds. This is going to give us a total distance, 8 times 5, of 40 meters. Seconds canceling here. So we can do that algebraically. We can also do that graphically. Now this is going to be the same graph. I'll show you a little bit of a different way of how to do this. You need to be able to do both. We have speed on the y, We'll set this up the same way. Let's see, we went by ones. In this one we went by twos, meters per second. Seconds, did I put those up there? Shame on me for not using my labels. Trying to move quickly here, no excuses. 6, 8, 10, 12, 14 meters per second. And that graph started at 1,3 and ended at 613. That one might be better than the previous one. I'll take it. Now, in order to use this, using the graph provided, so we're going to do this graphically, we can kind of break this up into a couple different shapes here. So the distance traveled by this object is going to be equal to the distance under the curve, or under the line there. We have another rectangle here. I'll try and draw this carefully. Now the area of a rectangle is equal to the base times the height. The area of a triangle is equal to 1/2 the base times the height. So let's try this. We'll start with the triangle first. Area of a triangle is 1/2 base times height. The base of this triangle is going from seconds of 1 to 6. That's a total of 5. And the height, we can call that 5 seconds. And the height is going to go from 3 meters per second to 13. That's 10 meters per second. I'll leave units in there so you can just kind of see what happens here. 1/2 times 5 times 10. What do we get there? 5 times 10 would be 50. Seconds will cancel. We'll be left with 50 meters. This is going to come out to the area being 25 meters. Now we're going to combine that with the result that we get from the lower rectangle, where we said the area was equal to the base times the height. The base of this rectangle would be the same as the base of the triangle, which would be 5 seconds. The height's going to be a little bit different. It's going to be 3 meters per second. 5 times 3 comes out to 15 meters. So area equals 15 meters. Now we combine these two. 25 meters plus 15 meters. Area equals 40 meters. And this gives us the same answer that we got prior. It won't always be as easy to use the algebraic method graphically. Might be an easier way to do this sometimes. It also might be required depending on the question. You might be asked to solve for the distance traveled by the object using a graphical method. I'll leave you with a joke for today before we get into acceleration type problems tomorrow. Where does bad light end up? In a prism. Have a great day.